Namaste. Again, this is Nataraja Pillai. I am going to discuss the classification of hypersonic vehicles today. Right? So, in the last class, we had a discussion on the hypersonic phenomenon, flow itself. Right? For example, we had a discussion on um, at what Mach number we can call the flow as a hypersonic flow, right? And from PL row, we had a discussion that if the Mach number is from 3 to 12, whatever it is, if there is the hypersonic phenomenon occurs, say the hypersonic phenomenon is like thin shock layer, entropy layer, then high temperature flow, viscous interaction, then low density flow, and so all those things. So if that occurs, then we can say that the flow is hypersonic flow. Now, we know the application of hypersonic flow in missiles, rockets, reentries, and all those things. But now we will have a look into different classification of hypersonic vehicles, right? So just a recap, yesterday we said these are the phenomenon occurring in the hypersonic flow, right? And I hope you remember yesterday we had a discussion on hypersonic uh, vehicles in comparison with supersonic vehicles and the subsonic vehicles, right? So we know that we have an imagination of the hypersonic design now, right? Like we can say that in the case of subsonic flow, the fuselage is really very big, and the wing has really a very big span area. Aspect ratio is good, like that. And when you come back to the supersonic flow, the nose is very sharp, and the wing is very thin, and something like that. But in the supersonic flow, like Doc from US, he initially considered the supersonic design to the hypersonic design, right? Right. And then he changed that, right? The hypersonic design was evolved, correct? So evolved in such a way that there is a blunt nose and so on. Now, today our idea is to classify, right? So before going to the classification, we need to know on what basis we classify. The first point is very clear. We know there are some special features of hypersonic flow. Then the second one, based on the trajectory and the configuration, we can classify. From the airplane design course, you might have learned that for any airplane, the mission requirement is an important one, right? Say, for example, you have designed the subsonic aircraft, subsonic passenger aircraft, where you have considered the mission profile like in the runway it should move and it should take off. Then there is a climbing phase, then a steady level flight, and then a descending phase, and then come for landing. So that was the mission, and based on that mission, you have designed. Again, some of you might have designed the fighter plane, correct? The fighter plane, remember, fighter plane, you are not simply considering the steady level flight during cruising. You might have considered various maneuvering, right? So that depends upon the mission. And hence, now we need to think about the mission requirement for hypersonic. So hypersonic vehicle, right? Because hypersonic vehicle also encounter various issues. So during the mission, so that need to be considered. Okay. Say there are some missions which are long flight, long duration flight. Um, so we need to have such a long duration flight with high angles of attack, blunt nose, and so on. And in certain cases, we have a low duration flight, and the nose should be sharp enough. to fly faster and so on. So in this case, we have a consideration in the re-entry flight. In the re-entry flight path, we have the two parameters we need to consider. One is ballistic parameter and another one is lifting parameter. These parameters are basically obtained from the momentum conservation equation, right? So the momentum conservation equation in the direction of the flight path and to the normal to the flight path. So by considering this, also we need to have a velocity altitude map of the flight, right? Um, so, and this knowledge of governing flight parameters and then the weight of the vehicle, surface area, and all these things are very important, right? Now, two things: ballistic parameter and lifting parameter. Here, the ballistic parameter we consider for a non-lifting re-entry flight path, say such as Apollo, capsule, and so on. Similarly, the lifting parameter we consider for the trajectories like the space shuttle. Right? So, based on these particular missions, we can now characterize or classify the hypersonic vehicle. The first one is re-entry vehicle. Second one is cruise and acceleration vehicle. Third one, ascent and re-entry vehicle. Fourth one, aero assisted orbit transfer vehicles. So we will see some of the examples for these particular classification and how it works. Okay. Now, to start with the re-entry vehicles, right? So these vehicles are typically launched using the rocket propulsion system, whether it is a solid rocket or liquid propellant, whatever it is, right? Then the second one is it is controlled by the control surface, right? Third one, large angle of most examples we can say is like the space shuttle from US, Buran, Russian one, and then Hope, Japanese one, and Avatar, that is the RLV reusable launch vehicle, that is the Indian one, and Hermes European Space Agency are some of the examples for the re-entry vehicle. Now, let us say one by one, right? So this is a space shuttle, and then this is Buran. So Buran was the first space plane to be produced by the part of the Soviet and Russian Buran program, right? So the construction started in 1980, and by 84, they have a full-scale orbiter which was rolled out. The Buran spacecraft was made to be launched on the Soviet Union's super heavy lift vehicle. I recommend you to search for this Energia. It is a super heavy lift vehicle which can take the Buran to the orbit and come back. For a reference, I have given the weight of the structures one by one, like structure and landing system, functional systems, propulsion system, and the maximum payload and maximum lift off weight. Right. I want you make because in the design of the airplane design, you have already studied the weight estimation, and hence it may give some information on the weight of the launch. Right. Now, I will go to the next one. Hope, that is Japanese re-entry vehicle, right? So the Japanese re-entry vehicle designed by having the partnership between the National Space Development Agency and the National Aerospace Laboratory of Japan. Later, these two organizations are clubbed into JAXA, that is Japanese Aerospace Exploration Agency, right? This project was eventually cancelled, but this was one of the conceptual one, and then they have designed it in a different way. Uh, for your information, you can see the space shuttle or Hope or whatever it is. Buran, all these has evolved design of blunt nose, right? Then coming back to the Avatar, that is the reusable launch vehicle. Um, I remember when I visited the Center for Airborne System, Bangalore, when I was a college kid like you. I have seen such a model was kept in front of the aerospace hangar, and they were telling something like, "This is a dream of Abdul Kalam, the former president and the scientist." Right? So this is a aerobic vehicle for trans-atmospheric hypersonic aerospace transportation, that is Avatar, right? So such a reusable launch vehicle, it is a winged configuration. It will be, taking off with the help of the rocket. Then it will go. There will be a combined coast phase, separated coast phase, and then go for descending, right? So when descending, the vehicle, the RLV vehicle only descends, and then it re-enters into the Earth's atmosphere, and it will be landing. Like once it comes into the its atmosphere, the vehicle will fly like another aircraft, and it will come for landing. But in this case, at present, the design is a splash landing in water, but they say that the runway length is not enough or so. But now in Indira Gandhi International Airport, the maximum distance of the runway is 4.43 kilometer, right? So it can land on runway also, right? Again, the next point here is like usually our Indian Space Research Organization, whenever they launch a vehicle to the orbit and you know they place the satellites into the particular orbit, they spend 5,000 US dollars per kilogram of the payload. Now, our thinking is to replace such vehicle by reusable launch vehicle, right? See, the idea here is when the airplane takes off from the ground, go to the orbit, and the orbit it can just put the satellites wherever we want, and then it come back. It's very interesting. Like it now, the whole launch vehicle will not be wasted and something like that. So they estimated that if that is so, we instead of 5,000 US dollar per kilogram payload, we can reduce it to 500 kilogram payload, right? 500 dollars per kilogram payload. So if that is the case, we reduce the cost by 10 times. That is the beauty of hypersonic vehicle. Hermes agency has designed. Initially, it was started purely with a French group, French project, but over a period of time, the finance is managed from the European funding agency, especially from Germany, right? Hermes was designed to take three astronauts to the orbits of up to 800-kilometer altitude on a mission of 30 to 90 days in space. So these are some of the re-entry vehicles um, which were existing, which was tried before. So let me go to the second classification, cruise and acceleration vehicles, right? So here, the slender configuration with low angle of attack flights are the main features of this particular type of vehicles, right? And these vehicles are prepared for high heating loads with ablative cooling system. We know that at the hypersonic speed, there is a formation of high temperature on the nose region, and the nose region will be the metal will be start melting out. So, right? So this is it is necessary to consider. Third point: the air breathing propulsion system of ramjet or scramjet type. are generally preferred for such vehicles. Okay. So one example of this is like Sanger, which is two-stage to orbit hypersonic vehicle. Has first stage of air braking propulsion when it is going into the atmosphere, and the second stage is propelled into the rocket. Right. So this is the model of the Sanger, right? Then the interesting profile of Sanger is like the silver bag. It was to be propelled down a 3 kilometer long monorail, having a rocket powered, and the amount of thrust is like 600 tons of thrust developed in 11 seconds. After taking off at a 30-degree angle, it reaches the altitude of around 1.5 kilometer. Then the speed of 513 meter per second will be reached. At this point, the main rocket engine would be fired for 8 minutes and burn 90 tons of fuel to propel the silver bird to a maximum speed of 6,138 meter per second. Right? So 6,138 meter per second, you can calculate the Mach number. Right? And the altitude of 145 kilometer, and see, some of the sources say that this can go up to 280 kilometer altitude. Now, see the Sanger as the aircraft accelerated and descended under the pull of gravity. It would even hit the denser air at about 40 kilometers. See, once the aircraft comes for re-entry, when it hits the Earth's atmosphere, it is like a very high density uh, air in the atmosphere, but beyond that, there is a very low density. Right? So from the lower density to higher density, it will be like a uh, skip, like it is almost like a stone skipped along the water. Um, I hope you remember when you go to the swimming pool and you are just jumping from some 10 feet or so. While jumping, you come fast to the 10 feet, right? 10 or 20 feet, and you will have a water of around, say, 5 feet or 6 feet. The height of the water may be small enough, but the density of the water is 1,000 times greater, right? So you are entering from 1.225 kilogram per meter cube density to the 1,000 kilogram per meter cube density. That is really, you can see the resistance offered by water and the air you can feel, right? So similarly, the higher temperature also encountered, right? So this is like finally the Sanger lands with a tricycle landing gear, and after traveling 23,500 kilometers, right? Then the third one is ascent and re-entry. So ascent and re-entry vehicle having an opposing requirement of their design due to the dual duty, right? Ascent and re-entry, right? So this is like dominated by the fuel requirement and re-entry by aero braking. Aero braking is nothing but offering resistance through aerodynamic design, right? So here the rocket or air breathing propulsion system can be preferred. And one few examples we can say National Aerospace Plane Program of United States, and then space plane by Japan, and hotel, that is horizontal takeoff and landing vehicle, are some of the examples of ascending and re-entry vehicle. We will say this is a national aerospace uh, plane program. So in this we can see, it is done by they say that it is the Rockwell X-31, and you know, it is a single stage to orbit vehicle like the one which we have seen before, right? Um, okay, so the second one is British Aerospace one. This is done in collaboration with the British Aerospace and Rockwell, right? So this is a horizontal takeoff and landing vehicle, right? And it perform the ascending and re-entry. Okay, so I recommend you to search on this particular horizontal takeoff and landing and National Aerospace Plane Program of United States. Okay, so have you noticed one thing throughout the discussion today? The classification of vehicles which can perform the re-entry vehicle, cruise and acceleration vehicle, and ascent and re-entry vehicle. And next one we will discuss about the aero-assisted orbit transfer vehicle. All these vehicles have certain things in common. It flies at hypersonic speed, and also it has a blunt nose, right? And we are discussing certain phenomena which is really happening in the hypersonic flight, right? So next point, we will come back to aero transfer vehicle. So aero assisted orbit transfer vehicle will make use of the braking on return from the or any orbit, right? So the minimum altitude of aero braking is 77.72 kilometer and the maximum of 121 kilometer with a duration of 480 seconds. Okay. So another problem here is at 85-kilometer altitude, if you see the density is highly irregular. You know very well that when we fly at a various altitude, the density decreases, right? And over a period, over a altitude, you will see the change in pressure, density, temperature, and all those things, right? So again, one more thing required in the hypersonic vehicle is like it travels at a very high speed, so that there is a huge temperature created. Say, for example, I can say that the temperature created, like for example, at 800 Kelvin, you can see that there will be a vibrational excitation takes place. Vibrational excitation of the air molecules around takes place, and that creates big trouble, right? Say, for example, at 2000 Kelvin, there will be a dissociation of oxygen takes place, right? So 2000 to 4000 Kelvin, we can see the dissociation of oxygen, and then more than 4000 Kelvin, the nitrogen dissociation starts, and it completes at 9000 Kelvin, right? And ionization at very high temperature takes place, say at 9000 Kelvin. So after 9000 Kelvin, we can say that the air becomes a plasma, right? The air becomes a plasma, then we need to think about the plasma dynamics and the behavior of real gas effects and all those things, right? So these hypersonic vehicles are experiencing the major phenomenal change of high temperature in shock layer, entropy layer, low density and high density ratios, and the formation of the plasma ionization and all these things makes the hypersonic spacecraft or vehicles a special one. Um, as I told in the previous class, it is not only the aerodynamics but aerothermodynamics, chemically reacting flows need to be considered in studying this hypersonic fluid, right? Okay, I this point for the today's lecture of classification of hypersonic vehicle. I recommend you to go through. Thank you very much. Again.